We'll now begin section 1.4 and discuss the complex number system. We begin with the definition for the imaginary unit I. The imaginary unit I is defined as I is equal to the square root of -1. In other words, I has the property that its square is -1. So in other words, as we begin to work problems, we want to remember these two things. We want to remember that I is equal to the square root of -1, and we want to remember that I squared is equal to -1. And actually these are the same two statements, because if you take your first statement, I is equal to the square root of -1, and you square both sides of the equation, then you get the second statement, I squared is equal to -1. We also need to define the square root of negative numbers. If a is a positive real number, then the square root of -a is equal to I times the square root of a. So what this is telling me is that if I have a problem, like maybe the square root of -9, which up to this point we have said that we cannot do as long as we are operating in the real number system. If we're going to use an imaginary number, we can rewrite the square root of -9 as the square root of -1 times 9. And we know that as our property of exponents that we can break this square root up, making it the square root of -1 times the square root of 9. Remember, our definition says that the square root of -1 is equal to I. So this part is equal to I, and the square root of 9 is equal to 3. And so the square root of -9 can be written as 3i. So let's look at a couple of examples. We'll begin with the square root of -16, which is similar to the example that we just looked at. So what we want to do is we want to think about the square root of -16 as being the square root of -1 times +16. We then want to break the square root up into the two parts. So the square root of -1 times the square root of 16. We know by definition that the square root of -1 is equal to I, and the square root of 16 is equal to 4. And normally we would see this written with the coefficient first, and so our answer will be 4i. Part B asks us to find the square root of -8. So again, we're going to rewrite -8 as -1 times 8. Furthermore, if I'm thinking ahead, I know that I cannot take the square root of 8. But if I break down the 8 into 2 times 4, I might be able to work with the square root of part of that, namely the 4. So now let's take this and let's break up our square root. We'll make it the square root of -1 times the square root of 2 times the square root of 4. So the square root of -1 will be I by definition. The square root of 2 has to stay the square root of 2. And the square root of 4 will be 2. So let me come up here. So our final answer is going to look like 2i on the square root of 2. Part C, we have I to the third, and we want to evaluate that. So what we might want to do in this case is we might want to break up this I to the third into I squared times I to the first. And we know that in this situation, if our bases are alike, we would add the exponent. So 2 plus 1 makes the 3 that we started with. Now, if we look back at our definitions, recall that I squared, we said, was equal to -1. And I to the first we know is just I. And so when we multiply -1 times I, we get -I as our final answer. What about part D? We have the quantity -I squared. And so what we may want to do in this case is we may want to rewrite our -I as -1 times I, and then square that result. In doing so, we know that the squared is going to apply to the -1, and it's also going to apply to the I. And so we have the quantity -1 squared times the quantity I squared. And so -1 squared is going to be a +1. I squared will simply be I squared. And so 1 times I squared is going to be I squared. And remember, our definition says that I squared is equal to -1. And so our final answer would be -1. Now, what they are doing with these last two examples is getting us ready to learn about the powers of I, and to recognize that the powers of I follow a pattern. So this pattern begins with I to the first, and we simply say that I to the first is I. I squared, we know by definition, and we've seen that in several cases here. Here's I squared, and we substituted in a -1. I to the third, we found to be -I. And I to the fourth, we could find to be +1. All right, and the reason why I to the fourth is +1 is, I'll come off to the side here and work it real quick. I to the fourth could be thought of as I squared times I squared. Each of the I squareds is a -1. And we know -1 times -1 is +1. So what happens with this is that the patterns begin to repeat. And so if the next one was I to the fifth, we would cycle back around and say that I to the fifth is the same as I to the first. And if we wanted I to the sixth, that would be the same as, we would go 1, 2, 3, 4, 5, 6 would be the same as I squared, so it would be -1. And so we see that this has a pattern to it that'll help us in working problems. We're going to come back to that in just a second as we look at our next example. All right, so we are asked first of all to compute the following powers of I, and the first one is I to the 9th. Now, just to make things easy, I'm going to write our pattern down over here. I to the first we said was I to the second we said was -1. I to the third we said was -I. And I to the fourth we said was +1. And now we want I to the 9th. So what we can do is basically on a low power like this, we could just count it out. That's one approach that we could use, remembering that this is a repeated cycle. And so as we count, we're going to count up to 9. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9 is back up here. Okay, and I'm just trying to write that down just to be sure that you see what I'm doing there. We're going to go 1, 2, 3, 4, and then back to the top, 5, 6, 7, 8, and then back to the top. And this will be I to the 9th. And so I to the 9th is the same thing as I to the first, which is equal to I. Okay, so now that's great and works really well for low powers. And we certainly could do it for 28. but it might take us a little bit of time. So we might want to think about a better way to do that, but I certainly could do it. I could say 1, 2, 3, 4, circle back to the top, 5, 6, 7, 8, circle back to the top, 9, 10, 11, 12, back to the top, 13, 14, 15, 16, back to the top, 17, 18, 19, 20, back to the top, 21, 22, 23, 24, back to the top, 25, 26, 27, 28. So here we are at I to the 28th and saying that that's equal to 1. And so even if you could convince yourself that it makes sense to do that for I to the 9th and I to the 28th, when you get to part C where it says I to the 102, we don't want to take the time to count that out. And so what we need to do is figure out exactly how this pattern works. So we want to keep in mind that if we have a multiple of 4, that all of those multiples of 4 land on this bottom I to the 4th. All right, so think about that. Think about your multiples of 4. We would have 4, 8, 12, 16, and so forth. And think about counting it out. 1, 2, 3, 4 would be on the bottom. 5, 6, 7, 8 would be on the bottom. 9, 10, 11, 12 would be on the bottom, and so forth. So we know that these are the multiples of 4. And so furthermore, what we know is that if something is a multiple of 4, when we divide it by 4, it divides evenly, which means that there is no remainder. All right, so look at the 28 that we had here. If I take 4 and divide into 28, I get 7 with no remainder. So that tells me that this 28 was a multiple of 4. It tells me that I should be here at the bottom on the 1. All right, so let's try that with 9. If I multiply or divide 4 into 9, it goes twice, leaving me a remainder of 1. All right, so 4 times 2 is 8. So 8 would have been right here on the bottom. And we need to go 1 more, so we would be back up at the top with the I. All right, let's try 102. So if I divide 102 by 4, 4 goes into 10 twice, leaving me a remainder of 2, and I drop the next 2 down. 4 goes into 22, let's see, what do we have, 5 times? Four times 5 is 20, and the remainder is 2. So again, if we had done 25 times 4, that would be 100. If we were at 100, we would already be right here. And then we have 2 more to go. So 1, 2, and we're at the -1. And so our answer there would be -1. And so that's going to be the easiest way to do it, is going to be to divide these numbers by 4, keeping in mind that an even division would put you on the bottom, and then looking at your remainder to see how many more you need to do. All right, so once we have an idea of how the I's work, we then move into talking about complex numbers. And so we say that for any 2 real numbers, A and B, the sum A plus BI, so this is the format for a complex number. The number A is called the real part, and the number B is called the imaginary part. So you might have something like 5 plus 7i. That is a complex number. The 5 is the real part. It sits by itself. The part that sits next to the I is called the imaginary part. So the real part is 5. The imaginary part is 7. All right, so let's look at some basic problems here. They're asking us, first of all, to simplify the following complex number expressions, and we begin with 4 plus 3i plus -5 plus 7i. Now, these start out very basic and easy. The idea is that you want to combine like terms, just like you would do if you were dealing with a linear equation with an x. So we will combine the 4 and the -5. So that gives me a -1. We will combine the 3i with the 7i, which gives me 10i. Okay, and we are done with it at that point. All right, so part B does the same thing, except it's a subtraction. So negative 2 plus 3i minus negative 3 plus 3i. And again, we would do the same thing as if we were dealing with an x in a linear expression. We would need to be careful with that subtraction sign, and we would want to distribute this subtraction sign through the parentheses. So we would have negative 2 plus 3i plus 3 minus 3i. Okay, and again, we're going to combine like terms, so we will combine the real parts, the negative 2 and the 3, making 1. And when we combine the imaginary parts, the 3i and the negative 3i, those actually cancel out, and so all we're left with is the 1. So for part C, we have 3 plus 2i. This is a multiplication times negative 2 plus 3i. And so we're going to multiply using the FOIL method, just like we did with our linear expressions. So first times first is going to give me negative 6. Outside is going to give me positive 9i. Inside will give me negative 4i. And last will give me 6i squared. And so again, we'll combine middle terms. So negative 6 plus 9i minus 4i would be 5i plus 6. Now when we come to this I squared, we want to do a quick substitution. Remember, our definition for I squared is negative 1. So let's substitute that in. So let me come up here. So we have negative 6 plus 5i plus a negative 6. And again, combining our like terms, the negative 6 and the negative 6 make negative 12. Plus 5i. And the last part of this is also a multiplication. Even though it looks like a power as we start, we want to remember that 2 minus 3i squared is really 2 minus 3i times 2 minus 3i, where we want to do the FOIL method. So first times first, 2 times 2 is 4. Outside, 2 times negative 3i is negative 6i. Inside, negative 3i times 2 is negative 6i again. And last, negative 3i times negative 3i would be positive 9i squared. And so combining your middle terms, the two 6i's would make 12i. And again, we'll do the quick substitution for the negative 1 in going in for the I squared. So I have 4 minus 12i minus 9. Combining the numbers, 4 minus 9 is negative 5 minus 12i. All right, so we've now introduced the imaginary number. We introduced complex numbers. We've done some basic operations on those complex numbers. And we'll continue in our next segment.